Hi everybody. Today I'm going to talk to you about the second part of that video 27, which is all about the net force this time. So I've put a situation up here with another free body diagram. This is kind of a weird one. So here you have a fisherman who has just been ice fishing, and he has a sled, and apparently he's a very good ice fisherman because he has a pile of fish on top of his sled. And so as he drags his sled with this rope across the ice, I was wondering if we could take a look at what vectors are actually at work there. So I'm going to ask you some questions here, and you can test yourself as we go here. You can see I marked out all of the forces that are normally would be listed right there. So let's see if we can put those in place. First, always, anytime you have a free body diagram, you always want to talk about whether or not there's a gravitational force. And 99.9% of the time, it's going to be on the surface of the Earth, and therefore it must have a gravitational force. So which of these four is going to be the gravitational force? Of course, it's this guy. And so let's go ahead and list that off. That's the gravitational force right there. No big deal. So you can see it's downward, and it's the largest force that's listed right there. Because there's a lot of fish, I guess. I don't know. All right. So let's go to the second of the two vertical forces, and that is this one right here. So is the sled falling through the ice? No. Okay. This fisherman would be really sad if it did because all of his fish would be gone. So there must be some supporting force that's acting against the weight of the sled and all the fish. And of course, that is the normal force, right? That normal force. But I want you to notice something. Do you notice how this vector, as it's drawn right here, is actually significantly shorter than that vector as it's drawn right there? That's going to become important in a minute, so hold on to that idea. Don't lose it, okay? So here's the next thing. As he's dragging the sled, there must be some force that's opposing his dragging it, right? Even on ice, there's some friction and a tiny little bit of air resistance. And so we typically have this force that opposes the motion that is almost always going to be a friction force that we put on the going in the opposite direction of the motion of the sled. So we're going to have friction over there. And then last but not least, we have the force that he's applying with the rope. And so, of course, it doesn't have a subscript here, but we would know that this would be the applied force, right, like so. So that's the applied force. Now you notice something weird about this applied force. It's not perfectly horizontal. In fact, it's at an angle, and they give you what the angle would be right there. This happens actually quite often, that you don't have perfectly horizontal or perfectly vertical forces. Thankfully, we have a tool that we developed in the last unit to be able to handle vectors at angles. And so what we do is we take and figure out what the horizontal and vertical components of that force would be. And so here I'm going to draw them out here. So if you think about it, this angled force right here, right there, is actually partially vertical, like so, whoops, like that, and partially horizontal, like so. Oops, that last one was bad, sorry. There we go. I did it again. Okay, anyway, you get the idea. So there's some vertical and some horizontal. And so here's my question for you. If we ignore the fact that he's pulling along the rope, because of course the force that he's applying has to go directly along the rope, right? That doesn't make any sense for ropes. If you tried to pull in a different direction than the rope is actually stretched out, that wouldn't make sense. So think about this for a second. This vertical force has to be acting against something else, right? And so if you look at it, this vertical force here is up, and this vertical force, part of it, is up as well. And so what do you think would happen if I added this vertical force up here plus this vertical force up there? So I'm going to go ahead and redraw this one right here, like so. And this I'm going to give you is the applied force in the y direction. So I'm going to say F sub applied in the y. So that's what I have listed right there. y. And I'm going to redraw the normal force so that you can see it's down here. There we go. And so if I drew these right, what we'd end up with is that this total upward force and this total downward force would be equal to 0. They would cancel each other out. How do I know that? Because the sled is not flying up into the air, nor is it falling down through the ice. So I know the verticals must cancel out. Now, here's the next question. If I have this friction force right here, like so, and I have this horizontal right there, the applied horizontal in the x direction, right? I can compare those two because they're going in opposite directions, and I can ask myself if they're the same size. So I'm going to redraw them. Okay, so here's the friction force, right? That's the friction force going in that direction. And then here is the applied horizontal force, like so. Can you see that they're not the same size? I hope so. If they're not the same size, then when this one will cancel out this much of that force. And so what will be left over is just this one. And so if I wanted to, I could redraw that as a force like this, and I'm going to change my color here so you get the idea. I'm going to draw it in actually green, I think. So I'm going to draw it in here, and it's going to be the same size and in the same direction as what's left over from this applied X force. I think I did pretty close. What is that name of that force right there? That name of that force is what's left over after all of these have been canceled out. These two verticals canceled this vertical, this horizontal canceled some of that horizontal, and what's left over is just this force. What do we call that? We call that the net force right there. And so I'm going to go ahead and write this F net. What does the net force do? Right down here. A net force causes a change in motion. What we would say, instead of saying a change in motion, to make it more specific and more physical, is it causes an acceleration. Accelerations can be speeding up, they can be slowing down, or they can be turning. What do you think this one's doing? Well, is it turning? It's hard to tell from this, but probably not, right? So it looks like this is all in one coordinate plane right here, where there's verticals and horizontals, but there's no into the page and out of the page, right? So sometimes you'd have an into the page and an out of the page force, but not in this case. So it must be just going to the right. So if there's an extra force that's going to the right, what do we call that? We call it the net force. It causes an acceleration. And since the motion is already going in this direction, right, that's the way he's pulling it, so it makes sense that it's already moving in this direction, then that extra force, that net force, must be causing an acceleration, which means it must be speeding up. Okay? Makes sense? If instead he was now, let's say he just let go, so that there's no force pulling in this direction anymore. So what you'd see is that the normal force would immediately become bigger again, and it would balance out the gravitational force. So there wouldn't be any change in motion in the vertical dimension. But there still is this friction force that's left over, and there's nothing to cancel it at that point. And so what would happen is the sled, which was moving, would slow to a stop. And that's what confused so many scientists for so long, is that they didn't realize that there was actually a force that was causing the change in motion. This friction force that was causing change in motion. A lot of scientists used to believe that objects just want to be stopped, right? They just want to be at peace, at rest, and you should just leave them alone. But that's not the case. We know that objects just want to stay moving however they're moving. And if you leave them alone, they'll just keep moving in that same way. Or if you balance out all the forces, they'll keep moving in that same way. But friction tends to be not balanced sometimes. And so especially if you stop doing what you're doing, that friction force wins, and it ends up slowing the object down. Also, if you look at a diagram from a car's perspective, and let's say a car, there's a road like this, and here's your car, like that. You have to apply a force because your car wants to move this way, but you need it to go around in the corner there. So you actually have to apply a force with the wheels in this direction. And that net force in that direction is going to cause the car instead to follow a curved path rather than the straight path that it really wants to. There's nothing that's balancing out that net force that you applied when you turned the wheel of the car. By turning the wheel of the car, the wheels in front turned, and therefore they applied that net force towards the center. We're going to spend a whole unit talking about circular motion and centripetal forces like this one, so I don't want to waste your time right now. But again, net forces cause a change in motion, which is an acceleration. That's going to become huge when we talk about Newton's second law coming up soon. Thanks for watching.